Hi everyone, welcome back. In this episode, we'll be talking about job scheduling, and our goal is to minimize the total wait time for scheduled jobs. We are going to take our inputs to be end jobs. Our inputs will be end jobs, and each of those end jobs would be executed in times T1 for job 1, T2 for job 2, T3 for job 3, all the way to Tn for job n. Our assumption is that this is not sorted. It's not sorted. We have a single processor. So the question is, how do we schedule these jobs in such a way that we have a minimal total wait time? So first of all, let's define wait time. Our wait time for job 2 would be T1. The wait time for job 3 would be T1 plus T2. Our wait time for job 4 will be T1 plus T2 plus T3. So this can be written as, we say, wait time for I a total wait time for job I would be this. You have one to I, and we can also say that our total wait time would be T waiting time of each job. So this is our total wait time. So right now we are going to be thinking about the algorithm that would give us a minimum total wait time for all jobs. If you can pause this video for a second, think about it, and get back so that compare what you thought about to the next part of this video. So the algorithm we are going to consider is the shortest job first algorithm. So what this implies is that we start from the shortest job, and after the shortest job we do the next shortest job, and after that we do the next shortest job. And we are going to use this algorithm in the hopes that it's going to minimize our total wait time for all jobs. For example, if we have jobs that take, this should be seconds. This is just an example. And if we do this job in this order, right? The wait time for this job would be 15 seconds. But supposing we do shortest jobs first, that means we start from the 1 second job, then the wait time for this same job is just 1 second. So we see that we have minimized the total wait time for this job. Okay, so let's try to investigate what happens when two jobs swap places. And before we start this investigation, I also want to mention that this algorithm is greedy. It's a greedy algorithm, and that's because it doesn't just follow one rule all through. At each step, it stops, then chooses the best option for it. After it does a job, after each job, it stops, then it chooses the next best job for it. So let's go on to investigate this. So let's imagine that we have jobs. All of these are jobs, some jobs. At this point, we have TI, that's a time for job I, time for job J, and some other jobs this way. And let's say that the time from here to here, that's the wait time for I job. It's let's call it C prime, right? This is I job, this is J job. Now let's swap this. Let's go on to swap it. When we swap this, we have all of this doesn't matter. At this point, we have TJ, then TI. This is J's job, I's job, then the rest. From this point to this point, nothing changes, right? We still have T prime. So what happens here? Let's check out the wait time. The total wait time of all jobs for this one up till I will be T prime plus TI, everything up to here, and the total wait time up to TJ would be T prime plus TI plus TJ. Let's look at this. The total wait time up to TJ would be T prime plus TJ, plus the total wait time up till TI would be T prime plus TJ plus TI. I want to find out if this is greater than or is this less than this. So let's check this out by exchange. Let's use our proof by exchange property. I'm sure we've seen this proof over and over and over again. For optimal algorithm, let's call this optimal algorithm, and let's call this new algorithm, right? So we are going to be working with the assumption that TI, that's the time for job I, is it's greater than the time for job T. So if that's the case, we have a new schedule, right? And in this new schedule, we say since TI is greater than TJ, we're gonna swap places. We're gonna swap the two jobs. So now we want the job J to be done before the job I. So this is the swap. So the waiting time of all jobs will remain the same, except the waiting time for I and for J. When it comes to the new schedule, we see that from here to here, for both for the OPT and for the new schedule, remain the same. But now the total the waiting time for all jobs, including I, and the total wait time for all jobs, including J, are now different. So for the OPT, for the optimum, we have this, and if to the right that we have 2T prime, because we have T prime plus T prime, we have our 2T prime plus, let's call TI, this is TI, oh, this is TJ. So we have TI plus TJ plus TI. That's what we have for the OPT. And then for our new algorithm, we have 2T prime. This is T prime plus T prime. We have 2T prime plus, we have TI plus TJ. That's here, TI plus TJ. Then we have plus TJ. So we see that if we say that TI is greater than TJ, if our assumption is that TI is greater than TJ, it means that our new algorithm has a smaller wait time than the OPT. I hope this is really obvious. If TI is greater than TJ, it means that everything from here to here for the both algorithms are equal. But the only difference is that for the OPT, we have a TI, and for the new algorithm, we have a TJ, right? And if we say TI is greater than TJ, it means that the OPT, the wait time for the OPT is greater. This is greater than the wait time for the new algorithm. So this means that when we work with shortest jobs first, the total wait time for all jobs decreases. So as TI is greater than TJ, I'm just recapping now. As TI is greater than TJ, the total wait time for the new schedule does not increase. So this does not increase. This is smaller. The total wait time for the new schedule is smaller than the total wait time for the OPT. So in this way, when we exchange all pairs, we obtain the greedy schedule, and the greedy schedule is the most optimal at this point. This new schedule, which is a greedy schedule, is the most optimal at this point. I hope you enjoyed this video. If you did, please remember to subscribe and like, comment, and I will see you on the next one.